Hello everyone and welcome to this next presentation, which is all to do with the graphs of trigonometric functions, in particular the graphs of sine x, cosine x and tangent x, and we're going to look at all three in turn. So we'll start with the graph of y equals sine x. What I've done here is I've set up a table with some angles that are measured in degrees from 0 up to 360, and I'll give you a few seconds on your calculators. Can you work out the values for y? And when you have done that, you can press play again on the video and I will go through some answers. Okay, good. So if you've done that correctly, and make sure that your calculator is in degree mode when you perform this action, you should have these values here. Now these values have been written to 2 decimal places. Obviously, if you've written it to 3 decimal places, that would be absolutely fine as well. Okay, and there are clearly some key features that are coming out from those values, but we'll discuss them once we have plotted the values on a pair of axes. So here are my axes. I only need to go up to 1 and down to -1 on the y-axis, and I'm going from 0 to 360. And if I plot those values, what we find is we get this curve that you're seeing here. And then I'm going to join those together in order to create my sine curve. And clearly I could carry this on and I could work out values for angles that are more than 360 and indeed less than 0. But we will talk about that in just a moment. One thing I will say about this curve is, yes, you are going to need to know what it looks like. You're going to have to be able to transform it using the transformations that we learn at A level. We'll talk more about that a bit later on. But if you were to sketch this curve, then for the basic sine x curve, it's often useful to look at multiples of 90. So there is always something important happening at 0, 90, 180, 270 and 360. And if you know the values for those key features, you can generally draw the curve in between those points. So 0, 90, 180, 270, 360 are key values of x when we are plotting the basic trig curves. Okay, so what do we know about the sine x curve in terms of its characteristics? Well, number one, we call it a periodic curve because it keeps repeating. So we earlier on plotted the curve between 0 and 360, but as we said, if you carry it on to the right, if you carry it on to the left, you can see that it produces this periodic cyclical curve, which goes on, of course, forever and ever. Now, how often a graph repeats itself is called the graph's period. So for this particular curve, for sine x, if we take 0 as our starting point, by the time we get to 360 degrees, it starts to repeat itself. So the period of this curve is 360 degrees. And that's going to be important later on when we start to solve equations that involve the sine x curve. And this little graphic just demonstrates that it doesn't matter where I choose my starting point from. You can see that by the time it does repeat itself, it has moved on 360 degrees. So the period is 360 degrees no matter where your starting point is on the curve. The other characteristic that we can talk about in terms of the sine curve is that it has rotational symmetry about the origin by 180 degrees. Now at school, you will have perhaps called that rotational symmetry of order 2, but at this level we talk about the order of rotation being by 180 degrees. So we can see that if we rotate the curve through 180 degrees, we find that the pattern for the sine curve is exactly the same. Okay, so moving on now to the second of our trig graphs, we're going to now look at y equals cosine x, or y equals cos x for short. So once again, 0 to 360, Again, the key features on this curve are going to be the 0, the 90, the 180, etc. But I have included 15, 30, 45 and 60 just so that we can see in detail what's happening near the origin. So a couple of minutes, make sure your calculator is still in degree mode, and can you work out these values for y? When you're ready to move on, just press play on the video. Okay, and again, if I just simply tell you that these values have been written to 2 decimal places when appropriate, obviously 0.5 is an exact value, as is 1, 0, -1, 0 and 1. And here is my my set of axes. We're only needing to go up to 1, down to -1, and 0 to 360 along the x-axis. And I'm now going to plot those points, and what we find when we plot those points is we get a very similar curve to the one before. We get this periodic cyclical curve. We'll talk more about the characteristics in a minute, but we have found from this activity that the starting place on the cosine curve is different to that on the sine curve. So the sine curve started when x is 0, started at the origin, whereas for the cosine curve we have a starting point of 0, 1. So that's quite often useful to remember when you're first learning about the sketches of these curves. But again, 0, 90, 180, 270, 360, they would be the key features that I would be working on if I was sketching the basic graph of cosine x and then filling in the details around those key values. So let's move on to the characteristics of the cosine curve. So again, we can see that it is periodic. It has a period of 360, the same as the sine curve. It's just that the cosine curve starts in a different place. And in terms of what's happening near the origin, in terms of a characteristic, we can see that the graph of y equals cosine x is symmetrical in the y-axis. And you can see from this graphic how that works. And that completes cosine. So we'll now move on to the final graph that we'll look at in this presentation, which is the graph of y equals tan x. And again, much the same. We've got the same values of x that we have had for the previous two. What I'd like to do is spend a minute finding those values for y, please, and writing them in the table. And when you're ready, you can press play on the video for me, please. Okay, and again, these values that I'm showing you here have been rounded to do 2 decimal places. But we have some interesting features that are happening in this table that we did not have in the other 2 tables. And that is that your calculator for certain values of x will have given you an error message, or in which case we say that the value of the curve is undefined for those values of x. And it's only when we sketch the curve that we understand why there are certain values of x that are undefined. So here are my axes again. You will notice that the requirement is that I need to go higher than 1 and -1, unlike the sine and the cosine curves. And if I was to plot these points that I found, I can see that there is a very different shape altogether compared to the sine x and the cosine x curves that we've looked at previously. So what it means exactly is that these values of x for which the curve is undefined at 90 and at 270, and of course there will be other values as well, what we have is we have an asymptote at that point. In other words, we have these imaginary lines, which we're showing here with dotted lines, where the curve approaches but never reaches. And then we have a value of 0 for when x is 180. Again, we have an asymptote at 270, and we have again a value of 0 at 360. So if you wanted to find out some more values in order to determine in a little bit more detail what these curves would look like, then that would be fine. But what we do get when we do that is a series of curves that look like this, that are heading towards the asymptote, both in a positive vertical direction and a negative vertical direction. And you would always make sure, of course, that when you sketch these curves yourself, your curves do not touch the asymptotes. They're the imaginary lines that the curve is heading towards. So a very different looking graph to the ones of sine x and cosine x that we looked at before. And then, as with the other two graphs, there are some characteristics that we can look at. So the most important, perhaps, of these characteristics is that the period of the tangent curve is no longer 360 degrees. We can see from this little diagram that the period is 180. The graph repeats itself every 180 degrees. And if you wanted to describe where those asymptotes are, then we can describe it using this notation here, which is quite clever. So n has to be an integer. So if n is 0, it means that there's an asymptote at 90 degrees. If n is 1, it means that there is an asymptote at 90 plus 180, which is 270. And similarly, if n is minus 1, then we end up with an asymptote of minus 90 degrees. And you can see from the diagram above that there is an asymptote at minus 90 degrees. So this is a clever way of expressing all of the asymptotes and where they are along the x-axis. So here they all are, described to us from that expression. And then finally, before we move on, a bit like the sine curve, the tangent curve has rotational symmetry about the origin by 180 degrees, shown nicely in that graphic there. So if we turn our page through 180 degrees, the graph of tan x looks the same as it did in the original version. Okay, good. So now that we've learnt the shape and characteristics of the three trig graphs of sine x, cosine x and tan x, it's now time to apply the work on transformations that we learnt a couple of weeks ago. And this is something that's important to do throughout your A-level because it's one of those topics that we often forget about. So if we are ever learning some new curves within the course, it's always important to apply those transformations to those new curves to keep that idea fresh in our minds. So we're going to have a look at a few examples, and then there's going to be an exercise at the end that you can have a go at yourself and see how you get on. So the first example that we're going to look at is this one. So the requirement here is to sketch the graph of y equals 3 sine x in the interval from 0 to 360. And I'll say a couple of things about that before you have a go. The first of those points is the fact that we have that interval, because if we didn't have that interval, then of course we would not know how far or how large to draw this curve as it goes on forever in both directions. So the interval of 0 to 360 is important. And the other thing to note is we have to make that decision about what is going to happen to the original graph of y equals sine x if we have a multiplier of 3. Now for this first example, I'm going to remind you of what that transformation would be, and then for the others you're going to make that decision yourself and then draw the subsequent new graph. So if we have a multiplier of 3 for the whole function, so it's the whole of sine x being multiplied by 3, then that would represent a stretch in the y direction or along the y-axis by a scale factor of 3. Because it's a y direction transformation that's taking place, there's nothing really unusual about what's happening here. Each of the outputs of the original curve are being multiplied by 3, which is creating that vertical stretch of scale factor 3. So spend a few seconds, a minute, just sketching the new graph on your whiteboards, please. Pause the video, have a go at that, and then when you're ready, press play, and I will show you the answer. Okay, so here is the solution. We have a dotted curve, which is the original graph of y equals sine x. And then our purple curve is our new transformed curve. So you can see that the x-intercepts are exactly the same as they were, because there's no stretch in the x direction. This is purely happening in the vertical direction. And each of our outputs has been multiplied by 3, creating that maximum height of 3 on the y-axis and down to -3 on the y-axis. Now, in terms of a sketch, what key features would you need to show? Well, clearly the curve would need to be shown. You would need to show that the curve goes up to 3 and down to -3, and then I would expect again those key features of 0, 90, 180, 270 and 360 to be shown on your sketch, even though some of those values aren't shown on this one. Okay, so here's number 2. What I would like you to do, please, is to tell me, number 1, what is the transformation that will take place on the graph of y equals cosine x? And then secondly, I would like you, once you've worked that out, I'd like you to sketch the new curve between 0 and 360. If you need to look back at your previous notes on transformations to make that decision, well, now's the time to do that. So press pause, and when you're ready for an answer, press play, and I will give you that answer. Okay, so by replacing x with 2x, the multiplier is only on the x, not the whole function. It means that we have an x direction transformation, and that x direction transformation will be a stretch in the x direction by scale factor 1/2. Remember, if we have an x direction transformation, then there's always something unusual about the transformation that's taking place. And in this case, the multiplier of 2 is creating a scale factor of 1/2. And in terms of the graph, you can see that the red dotted curve represents the original y equals cosine x, and the purple graph represents our new curve, which is a stretch in the x direction, scale factor 1/2. So in that 360-degree interval, the curve is repeating itself twice rather than once. So in terms of the values that you would need on your sketch, again, 1 down to -1 would need to be shown on your axes, but this time I would be writing the key features of 0, 45, 90, 135, 180. So even though those values aren't shown on the x-axis here, I would be showing them on my sketch when I was performing this in an exam or on an assessment. Here's our next one, so you should now get the idea of this. So I would like you please to look back at your notes if you need to. Tell me what the effect is of the -1 placed on the end of the function, and then I'd like you to sketch that curve in the interval of 0 to 360. When you're ready, press play on the video and we will go through an answer. Okay, so first of all, what happens with that -1 on the end of the function? We have a translation by 0 minus 1. The whole function is going to move down by 1 unit. So each of your outputs from the original cosine x curve are going to have a 1 subtracted from them, which creates that movement of 1 unit down on the y-axis. Again, we only need to draw this curve between 0 and 360. And if you've done that correctly, you will find that your curve looks like this. Now, the -1 is quite a common question on exams because you will notice that the original point of 0, 1 shown here on the y-axis will then, if we move it down by 1, will actually then be at the origin. So the examiner, the mark scheme, would definitely want your first point to be exactly at the origin, based on that translation of 1 unit downwards. And what that means then, of course, is by the time we get down to the minimum point on the curve, rather than it being at -1 originally, it's now at -2, so that would have to be shown on your sketch. And then as it increases back up to its maximum point here at 360, we are now again at the x axis rather than anywhere else. So by translating the curve by 1 unit, there are some exact specifics that need to be shown on your curve that I've just mentioned. So we would need to have it starting at the origin, going down specifically to -2, so -2 would need to be shown on your y-axis, and then back up to the x-axis by the time we reach 360. But again, I would be putting the values of 0, 90, 180, 270, 360 on my x-axis, and I would need to be showing that it's going from 0 down to -2 on the y-axis. Okay, good. So here is the last one. We have an interval again of 0 to 360, and what I would like you to do, please, is write down what transformation would get me from the graph of y equals tan x to the graph that's shown here, and then once you've written down that transformation on your whiteboards, have a go at sketching it. So press pause, have a go, and then when you're ready for the answer, press play. Okay, good. So the transformation this time, if you're replacing x with x minus 30, would be a translation to the right by 30 units. Again, because it's an x direction transformation, there's something a little bit unusual. So yes, it's a translation, but the vector for the translation represents that of a movement 30 to the right. Now, when you are sketching that curve, it can be quite tricky to know where exactly those curves should be drawn on your new pair of axes. So what I would suggest you do is, and this goes for any tan graph that you might have to draw, is I would suggest you draw the asymptotes in first, and then that will make it easier for you to decide where the tangent curve should be drawn. So instead of having your asymptotes at, for example, 90 degrees, you now have an asymptote at 120, and instead of having an asymptote at 270 degrees, you've now got an asymptote at 300 degrees, and I will draw those vertical dotted lines in at those points, and then it will make it far easier for you to then be able to draw your tangent curves. The other key feature, of course, that we can place on our diagram is that instead of the tan curve now going through the origin, it will now be going through the x-axis at 30, and instead of going through the x-axis at 180, which was the original, it will now go through the x-axis at 210. Okay, so there's two things we can do to finish off this presentation. The first of which is to have a look at this exercise here, and then there is an exercise that you can have a go at from the textbook. So this is a bit like the exercise that we've just been doing, apart from what I'm showing you now are the transformed graphs, and you have to tell me what are the equations of each of these graphs. And for some of these, there may be more than one answer, but on the whole, I will go with the answer that is probably the most obvious. But if there are two answers that I suggest could equally be used, I will show you them both. So have a go, press pause on the video, use your transformation skills and your knowledge of what the sine, cosine and tan graphs look like, and have a go at deciding what these graphs would have equations of, and press pause, and when you're ready to go through the answers, you can press play again. Okay, so we'll start with number 1 in the top left hand corner. What we've got here is the graph of cosine x, which starts at 1, goes down to -1 at 180, and then goes back up to 1 at 360. And what's happened to that curve is that the whole graph of cosine x has been shifted up by 2 units. It has gone through a translation of vector 0, 2. So the effect of that in terms of the equation is to place a +2 on the whole function. So you can either write it like you're seeing here, or you can write it as y equals cosine x and then plus 2 on the end of the function. Number 2, in the top right hand position, this is the graph of sine x as it's starting at the origin, but instead of repeating itself once every 360 degrees, it's repeating itself 3 times during that period. So there has been a stretch in the x direction, scale factor a third, and that would be resulting in an equation of y equals sine 3x. Number 3, 2 things are happening with number 3. The first is that it is the sine x curve, but it has been reflected in the x-axis. And you learned a couple of weeks ago that if you have a reflection in the x-axis, you simply place a minus at the beginning of the function. So all outputs that were positive become negative, and all outputs that were negative become positive. And as well as that, you will notice that there is a new maximum height of 2 on the y-axis and a new minimum height of minus 2. So it has been stretched in the y direction, scale factor 2. So again, that would represent the equation whereby we have a multiple of 2 at the beginning of the whole function. So y equals minus 2 sine x. Now, number 3, there are 2 possibilities. You can think of this as the curve sine x that has been translated 30 degrees to the left, in which case you will have this equation that you're seeing here. Or alternatively, some of you may have focused your efforts on the cosine curve, in which case it is the cosine curve translated 60 degrees to the right. Either way, there has been no stretch in the y direction, there has been no stretch in the x direction, the period is still 360, there is just a different starting point for the graph. So there has been a translation either of the sine curve or of the cosine curve, depending on which one you are happier with. Number 4, again, is based around the sine curve because it's beginning at the origin. And this time, rather than it having a period of 360 degrees, it actually has a period of 720. So it has been stretched in the x direction, scale factor 2, and that would result in the equation y equals a sine of a half x. And finally, probably the trickiest, what we've got here is the graph of cosine x, and it has been translated 1 unit upwards in the vertical direction, and then it has been reflected in the x-axis, and you end up with the graph that you're seeing here. So that's quite a tricky one. You can also write it, of course, as y equals minus cosine x and then plus 1 on the end of the equation. There are a few other alternatives for each of these, of course, if you've gone with a more a non-traditional method of going about it, but if you want any clarification, you can always ask your classroom teacher. Okay, and then finally there is an exercise that we can do on this topic. We can look at exercise 3.1 on page 72. That will test you on whether you understand what the curves look like, what their characteristics are, and also to do some more work on transformations. I cannot stress enough how important the knowing of these transformations is for the whole of your A-level. So the more practice you get on it now, the easier it will be when you revisit it later on this year and indeed throughout year 2 as well. So have a good practice of these skills, and I will see you next time for the next presentation. Thank you very much.